Thank you, Ami. It's really great to see all of you here. And I'm standing between you and lunch, so I will try and be as quick as possible. The basic idea of my talk is to essentially give you an overview of the work that we have been doing over the last decade or more to bring the kinds of technological innovations to a modern database. And that's going to be the focus. So I guess I can use this one. So I'm going to talk about 4 major design centers, as we call them. But these are all technical. So my talk is going to be focused on the technical architecture and the enablement that our product allows you to do to handle some of those great use cases that Subbu talked about. Now, if you look at what a database should be or what it is, essentially its goal is to keep data safe. That is the most important role of a database, and that's kind of what we focus on quite a bit. It's about strongly consistent transactions. It's about never losing your data on writes. The ability to actually work on providing what I would call as consistent reads, which the linearizable is the highest level of consistency we can offer in a single record system. Sesh will talk later about how we are going to extend it to multi-record transactions. But the basic idea is, keep your data safe. Once you do that, as a distributed system, I met with basically customers who are global here already. In the few minutes I was talking to people. I meet, every, Israeli company we worked with has global offices elsewhere and businesses elsewhere. So we need to have a geo-distributed active-active deployment, which is also strongly consistent. We'll talk a little bit about what that means to you and what we have done in that area. Fundamentally, Aerospike from day one has been interested in finding a better way to essentially build a database system that can, I would say, expand on the existing technology that existed before us, but to bring forward the new optimizations that are happening in hardware technology and how to take advantage of them for databases. We'll talk a little bit about that. And finally, there's a little bit about parallelism and indexing. These are basically, I would say, as fundamental concepts in accessing data. And we will talk about how we work on those areas. So first, let's talk about strongly consistent transactions. I'm not going to go into all the details of everything that's stated even in these slides, but definitely not into the details behind them, because we only have about probably 15 to 18 minutes left. But feel free to ask Zohar, myself, Sesh, anybody, technical in this, in Aerospike about more details on this, and we'll be more than happy to spend time with you on this, either, during the course of this particular summit or after that. The one point I want you to take away about our strong consistency algorithms is Aerospike algorithms are not consensus based. I mean, essentially it's consensus, but it's not quorum based. It is roster based, and I'll talk a little bit about that in the following slides, but that's kind of fundamentally what I want you to take away from this. There are other sub-bullets as, how do you kind of support failures, how heartbeats work, and so on, and how we maintain consistency. We'll talk about that in a little bit. But the basic idea is when a write happens to the database, we will write to all copies of the data. That is basically what we mean by not quorum based. Quorum means you can pick the number of copies you have to write and then you have to then deal with it during reads. We don't do that. And a lot of that, we are able to get away with this because of our performance implementation, the performance optimizations that we have done over the years. So we don't have to suffer the performance hits that most databases hit when they try to do this. And fundamentally, all you do is a client or an application generates a write request, which goes to every copy, and there's some parallelism involved. If you have more than 2 copies, then the first copy is written, and then the other 2 copies, the writes go in parallel. All of them have to be written before the commit is essentially sent back to the client. It's fairly straightforward. It's like two-phase commit, except that we don't follow, we don't use all the overheads of the two-phase commit algorithm. We've optimized it to make sure it's fast. Reads in the same way. If you want to actually provide linearizable reads, you have to look at the state of all the copies. It's slightly different than writes. You do not have to read every copy of the data, but you have to make sure the copy of the data you read from the master copy is in sync with the other replicas, so that you can guarantee that every write that's happened before this read is dispatched is actually incorporated into the read of the data that you actually are reading at that point in time. And that's again, and there are ways to relax this, so you don't need to have linearizable. You can get higher performance by using sequential consistency and so on. It's not important just to do the basic reads and writes. One of the interesting concepts is how do you increase availability while you're delivering strongly consistent access to data. This is actually a hard problem. And one of the potential pieces that help you is in building rack awareness. We discovered that maybe about 5-6 years ago. We implemented rack awareness support in Aerospike. A rack basically is all a rack essentially means is that two copies of the data aren't stored within the same rack. And that's kind of the basic invariant. And then you can have multiple racks. A whole rack can be taken out without no loss of availability because the copies are all existing somewhere else. That's kind of the idea. There's a whole bunch of details about it, but our algorithm works with rack awareness. And if you have multiple copies, then you can have the entire system available when a rack is taken out. Finally, there is a different model we use in terms of providing higher availability during failures, and this particular algorithm is based on rosters. What that really means is there are a set of nodes in the database that are essentially defined, if you will, to comprise the database system itself. These nodes have to exist, and when they exist, the database is whole and it's complete. Now when some of the nodes go in and out of the system, how do you maintain availability? One of the things that we have to essentially worry about is Lambert's theorem in the case of maintaining strong consistency replicated in a distributed system. You're supposed to have 3 copies, and Aerospike does not require. We've optimized our algorithms, so that the Aerospike does not require all 3 copies all the time. So you end up saving some level of hardware because our algorithms are sophisticated enough that when there are failures, we are able to materialize the 3rd copy, which is required to break ties and so on in terms of writes. And that's kind of shown. I'm not going to go into the details of Rule 2 because it will take too long. But there's a whole bunch of papers we published, as well as white papers which are available, which explain this concept of roster and why this actually increases availability during failures. And you will see that in the next section when I give you an example of a 3 site cluster. You'll see that in a minute. So one of the things about geodistribution, first of all, we need to be able to handle multiple nodes in the cluster. Pretty much it's table stakes that all of these modern databases have to have multiple nodes. They have to work together with each other to deliver all this database performance as well as availability and scale, for that matter. Now Aerospike has essentially implemented algorithms to enable data to move around in the database during node failures without affecting the individual read and write transactions. Many of you who are customers have already seen it. People who are who've not used Aerospike yet, this is basically one of the big, most important parts of Aerospike in terms of how you operate it. And we'll talk about how we can be more efficient in terms of hardware utilization a bit later. Now, here's an example of a synchronous active-active system that you can implement in Aerospike. This involves putting together a lot of the concepts I already mentioned fairly briefly. Essentially, you have 3 copies here with 3 sites, and this is distributed across both the US and Europe. You can't see any of the maps, barely visible in this, but just imagine that the racks, rack 1 and rack 2 are in the US, and rack 3 is somewhere in Europe. Now, what happens in this case is, if you can, the basic advantage of this is there are 3 copies and three racks and 3 sites. So all the apps can go locally using sequential consistency. So you don't have to cross racks in order to read data. So your applications can get sub-millisecond latency. Our writes, as I mentioned earlier, are not quorum based. So all writes have to go to all 3 copies, which means you probably will incur over 100 to 200 millisecond write latency. Now, this actually works for certain kinds of payment-based applications, which we are deployed in fact, in Europe actually, from Banca d'Italia and so on. But the point is, the more important point is, you can take down an entire rack and still continue with both availability and consistency on the other 2 racks. This is based on those roster-based algorithms I just briefly flashed a slide on. There's more detail behind it. So we can actually make that work. And there is no operator intervention required on a rack. Actually, in this case, this whole site is either unavailable or it's kind of down for whatever reason. Now, the other thing that happens is, when these sites are down, everything happens without operator intervention. But then, when the site comes back up, again, no operator intervention is required, and the system continues back to the original state. This is your synchronous active-active system, which kind of works well with Aerospike. The reverse of it, or the alternative way of doing this, is to have an asynchronous active-active system where individual clusters can communicate asynchronously. The technology we use is called XDR. I think one of our Israeli customers is going to talk about it later as to, we actually invented it for them in the first place. But the point is, that allows you to have links which are dynamic between clusters. You can filter across links, you can move data around, and you can actually manage whatever data movement you'd like to do within the cluster. The interesting thing here is, this is not strongly consistent. Essentially because a commit to one database will take some time before it appears in another database because of a data lag. Now, people can manage that, and then we can also, using certain techniques like bin convergence that we have implemented in Aerospike, you will be able to handle strong consistency, essentially eventual consistency is one term. I don't like to use the term, but the idea is a strongly consistent site can make the other site get to a strongly consistent state if you have connections between them and so on. And that actually is guaranteed. However, there could be potentially conflicts if you have multiple updates to multiple sites at the same time to the same subpart of a record. We can detect those conflicts, we can resolve them using last update wins. All of that means that you don't really have strong consistency. What you have is a level of availability which is higher than if you were to implement a purely, strongly consistent, globally synchronous active-active system. So here, there will be no write latency hits, and you pay for it using the lag. Let's get to some of the performance optimizations that Aerospike has done, which enables some of these algorithms I just talked about to work better in Aerospike than in comparable systems. And that's fundamental to why Aerospike is even being used in these strongly consistent applications. We started off by mostly in ad tech and various areas where high performance was important. But then we are bringing those high performance capabilities to the strongly consistent implementation that we have also added to and that's kind of fundamentally a game changer. Now, I'm not going to talk about the use cases, but that's something we can discuss apart from, outside of this talk. The hybrid memory architecture algorithm that we invented in 2009 was basically fundamentally the reason why myself and my co-founder, Brian Bulkowski, started the company. We decided that this would give us a 10x performance advantage and a 10x TCO advantage over everything else that existed out there. And it seems like it still seems to be true, which is somewhat surprising given that it's been like 12 years and for the last 8 years our code is actually open source. We do have patents to protect our technology though. But the basic fundamental idea here is very simple. You have SSDs and essentially they can do random reads. And we wrote up a file system which enables you to write large amounts of data by batching writes. Think of it as a log structured file system, you defragment on the back end, but it's a basics, it's an idea which works well with SSDs because it does not random read. So what have we done? Fundamentally at the high level, we have expanded the real-time footprint of data on a node to not just to the data resident in DRAM, but also expanded to the data which is stored in SSDs. So immediately you can now have tens of terabytes of data per node which are real-time, which means your cluster sizes for a petabyte scale has been reduced by 10x over anything else that's out there while providing real-time performance. Subbu talked about the PayPal experience of essentially figuring out what the fraud score is before a database, before a transaction is completed. In order to do that, you have to look at a lot of data. Before they used Aerospike, they needed to use like hundreds of nodes to do something which only took Aerospike maybe like dozens of nodes, like 25, in fact 20 nodes, I think. So the fundamental improvement for them was they could grow 10x. The 200 plus nodes they were using before came back to 20, and eventually they could go 10x in terms of their load, while providing the same, in fact they were providing 30 times better or fewer timeouts missing of SLAs. They were missing 1.5% and they only missed like 0.05% with Aerospike. This was like 5-6 years ago. And they've talked about it, okay? PayPal has talked about it over the years. And this is fundamentally a game changer. Now, if you look at, and what is the other thing it gives you? It gives you the idea of tiers. So as a, as basically as any of you who are deploying high scale real-time systems, which may or may not be strongly consistent, what we provide you is choice. It's not only choice today of what databases, what various storage technologies exist, but it's also choice like a new technology like Intel's PMM appeared and now it's disappeared. We used to support it, we still support it, but something else is going to show up with CXL. We will be there to support it. So you don't have to worry about it. You will get the choice. You will get the best possible implementations required for the kinds of applications you are essentially building without having to worry about dealing with all these various things. And you can make trade-offs here. And why is it important, right? It's important because it gives you a choice of trading off between performance and cost. You know, as you go up this thing, your performance increases, cost also increases. And then somewhere in the middle, if you look at hybrid memory, you know, you can barely read it here, but it's 99% less than 1 millisecond latency, and it is also able to essentially, have, the ability to run with a lower or a very affordable cost, right? It's cheaper in some sense than DRAM. So it's the best of both worlds to some extent, and that's important. And again, you can see by the list of nodes there, you can get in 6 or 7 nodes, you can run what would take like 37 nodes there. And this is all very conservative. There's a customer in Europe who basically reduced their 4,000 or 2,000 node cluster to about 300. So it's about, or less actually. Optimizations for CPU, memory, and network. This is really important. It is not enough to just put all your data in SSDs and hope for the best, because now it's all real time. You can do real time access to SSDs. What about the extra load you put on the CPU, on the network, on that node? Before, the node used to have a terabyte of data. Now it has like 25 terabytes of data, and which means proportionally, and you used to have like 100 nodes of the cluster. You now have 10 nodes. You're going to get 10x more transactions per second, which you have to push through each of those nodes. How do you do that? So we've spent a lot of time on transaction optimizations. We can actually push 15 million transactions a second. We worked with Intel once and we actually showed a benchmark on that. Does it mean you're going to need that? No, most people don't need that. But the point is, you need to kind of compensate for the fact that you're putting more real-time data on every node, and which means more transactions per node. And we did all the work, all written in C, and basically which, multi-threading, CPU pinning, NUMA pinning, whatever it is that you needed to do, we use block-based allocation and so on. And all of that is really important. So finally, come to the fourth section, how do you kind of build a database out of all this stuff? It is important to use classical database techniques. There are two fundamental techniques in databases which enable them to handle lots of data and also with some level of real-time performance. I don't even want to say real-time performance, some level of high performance. Because even if you go look back to like Oracle or DB2, and I used to work in those areas a long time ago, my background is in databases as is Sage, So they were also high performance systems in those days. Database is always about high performance, okay? But the thing is that what has happened with the internet and various other developments that have happened in terms of mobile technology is the levels of scale have shot through the roof. It is 10x, 100x, or more in many cases. We've had customers grow in scale to 200x over the last 10 years. I've observed, customers going through the same customer. When they started at 1x, they've got like 200x in like 6 years. This is probably, you've seen many of this kind of behavior within the work that you yourself do. Now, so you got to use all the technique, the basic techniques. It's all about parallelism and indexing. And Aerospike has a fundamental way of looking at data. We basically have a way to partition it. So the key space is partitioned into 4,096 partitions, which is what is shown here. 0 to 4095, and then we map these partitions individually to nodes. It's a 5-node cluster shown in the picture here. It's very simple. The partitions, or the map as we call it, the partition map, is based on the list of nodes in the cluster. Every node has the ability to kind of look at this map, and it's algorithmic. It's based on RIPE-MD 160. We find some bits and we figured this out. It is fully randomized. And when a particular node goes out of the cluster, in this case node C, all of the partition maps just pull to the left. There's one important subtle thing though. There are certain reasons why a partition map is written this way. Our original algorithm was to minimize data movement when nodes go in and out of the cluster. And we did that first. But what we found after when we started increasing the size of deployments to 200 nodes and so on is that because we minimized partition movement during the time a node comes in or out of the cluster, we ended up with skew during the runtime of pounding it with transactions, which means the system was a little bit unbalanced. So we then backed off of just minimizing it. We added a heuristic which also optimized the balancing. So we have a uniform balancing algorithm which we added about 5-6 years ago, which is the default right now. And that means a combination of this eliminates hotspots. See, our goal is to eliminate hotspots. It's not a specific algorithm. A distributed system can easily be brought to its knees if there's a hotspot in the system. And we have to keep working on that as we increase the scale. And that's the focus of this. Now, if you look at the Aerospike clients, we have what is called smart clients or fast clients. We share this partition map with those clients periodically. Typically once a second, the client pulls in and gets it from the cluster, which means that when clients send requests to the server virtually all the time, apart from the time when nodes go in and out of the cluster, they actually have the right node to send it to. It's on a single hop. This again helps us in avoiding hotspots. This is fundamentally one reason why Aerospike essentially is better than pretty much everything else out there in terms of performance. Now, the other thing is we introduced secondary indexes like any database, and we have revamped it in the last couple of years. Our original implementation, I'll be honest, this was like in 2014, didn't really provide us the level of support at scale that we thought we needed. So we have rewritten that over the last few years, and now everything in secondary indexes come out except secondary indexes in Flash, which Sage will talk about. So pretty much it's a new implementation, but fundamentally it is based on partitions. At some point we added an ability to run these queries on a per partition basis. Combining the parallelism and indexing is something really, really important for us, and we do that. Finally, right, the Aerospike has a massively parallel architecture. I talked about multi-threading with the processor, and then you align it with multiple disks per node, and then you can partition data across disks, just like you can partition data across nodes, and then across partitions, and then partitions across nodes, partitions across disks, and then you have multiple network queues. So think of it as like completely parallel and avoiding bottlenecks, so you can push heavy throughput through the system with low latency and strong consistency, because those algorithms, if you need the strong consistency, can push it faster than comparable systems. And that's what we are shooting to do, right? This is basically what you should expect from us, and you should challenge us to continue to do this. So to summarize, right, strongly consistent transactions as well as geo-distributed active-active system allows you to deploy systems at with strong consistency, which are also distributed. And the optimizations that we have done on the on modern system architectures enables you to handle workloads that otherwise you wouldn't be able to handle. Okay, so it's very important to understand, right? When you say that, well, you can actually handle it on Oracle, and it's actually true. The amount of money you would have to spend in terms of your memory and various other things in order to actually launch it is going to basically sink any startup. So if you say the only people who can actually use technology are the people who are already successful, like a Google or a Meta, nothing against them, that's not actually how the technology industry works. We do the opposite. We try to disrupt ourselves as much as possible, and that's kind of our goal, is to provide technology which is available to anybody, including a startup which wants to start up and become the next Google or Meta or whatever. And we have, I would say, a few dozen customers, in Israel especially, who've gone IPO, for example, and the US, in India, wherever, pick the country, where there is scale, or where you want to deal with scale like Israel does, right? This actually is the reason why we work on all this technology, and then the business and the fact that you're all here, to some extent validates the work that we have done together, so to speak, in solving hard problems. So, saying that, thank you for being here. Now we can go to lunch.